हेलो सर। हेलो।
বলো।
হ্যাঁ স্যার, মানে আমি স্যার আজ ক্লাস স্যার করতে পারবো না স্যার, আমার মানে একটা ডিভাইসের চার্জ নেই, কাল রাত্রেই ইলেকট্রিসিটি নেই।
ও আচ্ছা আচ্ছা,
হ্যাঁ স্যার।
ঠিক ঠিক আছে।
হ্যাঁ স্যার।
আচ্ছা, আমরা শুরু করি। আহ, কালকে তোমাদের সঙ্গে যখন ডিসকাশন করছিলাম তোমাদের ইন্টারনাল অ্যাসেসমেন্ট 2 এর পারফরমেন্স নিয়ে মোটামুটি কিরকম কি করেছো, একটা মেজর পয়েন্ট আমি ভুলে গেছি। সাম অফ ইউ actually have done it, so I forgot to discuss on that. So today I'm going to share this with all of you. First I will do it, then I will come back to my original topic of Fourier series. So let me share the screen. Everyone just see it. Can you see it, my screen?
Yes, sir.
Okay. Now look at this step. This step. Some of the students of this group batch has done this. Again, that representation of a unit step function in terms of the ramp function. So they first defined Rn as equals to n. It's a ramp signal which is n. That means it is valid for all values of n, because they have defined like this, just like this, Rn equals to n. That means it is valid for n equals to minus, n equals to 0, n equals to power plus, all the values. Then they, after defining this, they have represented or created a function gn in terms of this Rn minus Rn minus 1 divided by 1. Okay, now after that they have put the value of this function and its shifted version like this. Okay, then after subtracting n minus 1 from n, which reduces to 1, and then they have written this is equals to u of n. Now everybody just see, everybody carefully looks into it. Now tell me, after analyzing this step, whether this is correct or not. If not, why? If yes, then why? Based on this definition of Rn.
স্যার এখানটায় ওয়ানটা নেগেটিভের জন্য ভ্যালিড থাকছে, ওই জন্য কি মানে ভুল আছে?
ওয়ানটা নেগেটিভের জন্য ভ্যালিড থাকছে because the definition of Rn is like this, তাই তো? So it is valid for all the values of n. Okay, all the time index.
হ্যাঁ, আর যেটা
বলো।
যেটা ট্রু না, কেননা ইউএন শুধু পজিটিভের জন্য 1 থাকবে,
এক্স্যাক্টলি,
পজিটিভ অ্যাক্সিস।
from 0 n এর ভ্যালু 0 onwards, তাই তো? 0 and প্লাস ইন্ডেক্সের জন্য, টাইম ইন্ডেক্সের জন্য, প্লাস ভ্যালুর জন্য, পজিটিভ ভ্যালুর জন্য। সো তুমি কি করে এটা লিখতে পারো? এটা কি করে হয়? যারা যারা করেছো, some of you have done it. So just check whether it is correct or not. Technically, whether it is correct or not. This point. So one for all values of n doesn't mean it is a unit step. It's just a DC. Just a DC signal. Or not signal actually, it's a DC value. DC is not a signal. Anyway, so it is just a DC value. One for all values of n. If it is so. So it is wrong. But if you define your Rn, the way we define is n un. It is just a definition. Means only we are considering the positive half, 0 onwards for all positive values of n. So in that case, obviously for n equals to -1, your signal is 0. All values of the signal for the negative time index are 0. I mean, to capture or to get the sense of a causal signal, we have defined like this. Now, the point is, in that case, if you define like this, Rn minus Rn minus 1, then definitely it is not going to work for you. ঠিক আছে? First of all, এই জায়গাগুলো বুঝবে, টেকনিক্যাল জায়গাটা কিছু কিছু অ্যাপারেন্টলি দেখে হয়তো অনেক সময় মনে হচ্ছে ঠিকই আছে, but actually not right. So in this case, you cannot expect that you will get marks, any mark. So those who have done it got 0. ঠিক আছে? আচ্ছা, আরেকটা পয়েন্ট হচ্ছে, even though we define Rn like this, even though in the that I was trying to discuss in the last class, even though you have defined Rn like n into un, this is just a definition, and this definition only tells you actually Rn equals to n is sufficient if it is valid for all values of n. If the ramp function starts from -infinity and goes up to +infinity, then it is okay. Rn equals to n. That's simply Rn equals to n. But the point is, if Rn equals to n un, that means to get the sense of a causal signal, that means valid for the 0 and the positive values of the n, you are multiplying by un. That is the only reason why you are multiplying by un. This is not in that sense, because some of you have already done Rn divided by n to get un. That is kind of a representation of un in terms of Rn divided by n. That last class I was discussing. The point you should understand, this is not a representation of Rn in terms of un. Please note it. It is not a representation also. If anyone asks you to represent, if I just ask the question in other way, okay, that means represent Rn in terms of un. Suppose the question was in our case, the question was represent un in terms of Rn. If I ask you to represent Rn in terms of un, then this is not the answer. First you have to understand, this is not the answer. The answer would be what Archana has done. Rn would be, it will be un. I am writing and you will tell whether it is correct or not. Plus un minus 1 plus un minus 2 plus ... Is it correct?
Not correct.
Not correct. Why?
Sir, n equal to 0 তে এই definition অনুযায়ী 1.
Very good. I have written the term un. So if I write un, then obviously at n equals to 0, the value would be 1. Value would be 1. At n equals to 1, the value would be 2. Okay. So this is not Rn. If I have to represent Rn, exactly Rn, which is like this, n un, then in terms of un, what I cannot write this term. I cannot write u of n So what do you have to do?
Sir, I have written this formula for Rn plus 1. You
I
can check.
know, I know.
Yeah.
This is for Rn plus 1, it is okay. But if I want to write it for Rn, then how to write? I cannot write Un. Then how to write?
Yeah, then start from Un minus 1.
Exactly. Then start from Un minus 1. Exactly. Then start from Un minus 1. The first term will not be there. This first signal will not be there because you are basically sequentially adding. For each, giving a one sample delay, and you are adding the unit steps sequentially, one after another. And just you have to keep on adding. So here, for n equals to 1, you will get value of 1. And that is expected from a RAM. Here, for n equals to 2, you have one sample having a value 1 from this, and already from this another sample at n equals to 2. So both will be added and you will get 2. In this manner, it actually will get 1, 2, 3, 4, 5, 6, and so on and so on. And so this is a representation. But this is not a representation. Like you cannot say it is a representation of Rn in terms of UN. Okay, so these are the very subtle things you have to understand, and accordingly you have to represent. Anyway, those who have done it, just correct it. Okay. So today, in the last class, we did one example where we have shown that how powerful our Fourier series, the Fourier series is basically a mathematical tool, is how powerful it is, how effective it is, how efficient it is to analyze any LTI system. That means given an LTI system, the only task you have to do, you have to first find out the h of j omega. That is the, your transfer function of the system function for that system. And rest of the things are just you can do just by inspection, just by observation. So the term by term, you take each and every terms of your input and accordingly and apply the formula or the concept of eigenfunction, eigenvalue, and then you can write the output terms for each input terms, and then you can just add on the way the inputs are added. Okay, so no complicated mathematical operation is required. So that is why it is very powerful, very easily you can done it. Now the point is, in that example, actually probably you have seen that you actually what I say, you can represent your input, that is xt, which was 1 plus cos 2 omega naught t plus sin omega naught t, something like that. So you can represent that in terms of, as a summation of sine and cosine. That actually in turn can be represented as a summation of complex exponentials. Okay, but each complex exponential term is acting or behaving like an eigenfunction for that system. So it was very easy for you to identify that a case, that is the term that is associated with each exponential. Okay, each of the exponential. That was very much easy for you to identify that what would be the value of ak. That is a of 0, a of -1, a of -2, a of +1, a of +2. For the last example I've done. But now you think in general, suppose if the form of the xt, if xt is given in such a way that suppose it is very difficult for you to understand what are the values of ak. Then just by inspection, just by observation, just by looking into it, you are unable to read or capture the information regarding AK. It is not very straightforward. There may be some kind of graphical representation may be there. Some kind of, complicated, any kind of complicated functional form could be there. So from where it is not very straightforward. Okay, the way we did it in the last, that was very straightforward. Okay, so it is difficult. But then the question is how to find out AKs in general. How to find out the AKs. How to find out it in general. Now, for that, let me share this slide with you. Just to see. Our task is to find out AK. And we know এই তোমরা দেখতে পাচ্ছ স্লাইডটা?
হ্যাঁ স্যার।
ওকে,
স্যার খুব হেজি পিকচারটা।
হেজি একটু আছে, হ্যাঁ। এবার আরেকটু জুম করলাম, এবার ঠিক আছে?
হ্যাঁ স্যার, বোঝা যাচ্ছে মোটামুটি।
আচ্ছা, আমি রিড আউট করে দিচ্ছি, অসুবিধা নেই। xt equals to you know that the summation of k minus infinity plus infinity a k to the power j k omega naught t. You know that this way we can represent by periodic signal, any periodic signal. Now what do we have to do? We have to find out ak. This is the ak which you have to find out. It's a general expression, and we have to find out this. Now to find out this, what we are doing, we are basically first multiplying both the sides by e to the power minus j n omega naught t and integrate over time period t naught. So we are multiplying this side, left hand side, as well as right hand side by this e to the power minus j n omega naught t and integrate dt over t naught. This is a one time period. Any time period you can integrate. Okay. Now here, so here you have basically two things. One is the integration and it's the summation. Now you just think carefully, just by looking into this term, that t is actually a continuous variable. T is actually a continuous variable here. And it what I'm trying to say, it has nothing to do with the k. K is basically a discrete variable. K is basically a discrete thing. Okay. And t is a continuous thing. And they are kind of independent of each other. So this k, which is an integer variable and a discrete thing, you can take this out, this k, ak, out. So this summation over ak, you can take it outside the integration. And you just first carry out this integration first. And then I will come back to this ak related factors. So if you carry out the integration over a single time period t naught, then you know you can represent this in terms of the cos and the sine, and you know if you integrate over a one time period, when it will be zero always, not always zero, except when k equals to n. When it is k equals to n, then only what you get, if you put the limit, you will get t naught. And this sine term always results in zero, always, when integrated over one time period. So in this way, I can write that integration ultimately reduces to this: when k not equals to 0, it is actually, I'm sorry, it will be when k not equals to n. When k not equals to n, it will be 0. And when it is k equals to n, it is t naught. That is exactly the value of the time period. Fine. Now, just then what we can do, because ultimately we have to put the value here, because the term is summation over ak, then multiplied by this integration term. Now integration, the result of the integration comes out to be like t naught for k equals to n, and 0 for all other values. So, but here we are doing the summation over all possible values of the k, from minus infinity to plus infinity. Now we understand that this is a kind of, that integration within the summation. Okay, and the summation index or variable, whatever you say, that is the k, which runs from minus infinity to plus infinity in general. This actually occurs, this also, that we should say also occurs inside the integration sign also. Look at this, here also there is a k. Now the point is, this integration will give you a non-zero value only when k equals to your n. For all other values of k, actually it will give you 0. So then if this integration gives you 0, then when it will be multiplied by whatever the value of k, doesn't matter, it will always give you 0. So we will hardly bother with any other ak's where k is not equals to n. We'll hardly bother, because all the ak's will give you 0, because ultimately it will be multiplied by the 0 because of this integration. And so we will only bother about the ak where k is equals to n. So that means we can write this, that was the left hand side, which is equals to this is the right hand side. So right hand side ultimately reduces to n into t naught. because an means ak for k equals to n, and only for that value we are getting t naught from the integration. So the summation become immaterial, because the summation or the value, whatever you say, actually that only exists for k equals to n. For all other values of k, actually doesn't exist because it is multiplied by the 0. The summation reduces to 0. So only thing is that you just forgot about all those terms, all those symbols and notations, etc. Only term that will remain is an, and it will be multiplied by this t naught. So ultimately, if we just rearrange this thing, we can write an equals to 1 by t naught. T naught comes here at this side, 1 by t naught, integration over one time period xt to the power minus j n omega naught t dt. Now again, if you change the variable, you can replace n by any other variable like k. So you just replace by k. So ak equals to 1 by t naught, integration over one time period xt to the power minus j k omega naught t dt. That is the formula. In this way, we can find out, given any form of xt, whether graphically or any complicated mathematical or functional form, whatever is given, what do you have to do? You just first multiply that with e to the power minus j k omega naught t t and integrate over one time period and divided by that time period. That will give you ak. You change the value of k, then it will be another ak. You again change the value of k, it will be another ak. In this way, you are supposed to get all the ak's. Ak's, you know, that is the Fourier coefficient in this series. So whether that is for the plus value or for the minus, but then like in the last class we did now, a minus 1, that means k equals to minus 1. A plus 1, k equals to plus 1. A minus 2, k equals to minus 2. A plus 2, that means that the subscript. The k equals to plus 1. So actually the value of k is nothing but, you just see here, the value of k is multiplied with omega naught. So value of k is nothing but the frequency component, the integration of the frequency component. That means suppose when k is plus 1, then it is simply omega naught. So that means you can say it's the fundamental frequency or the first harmonic. When the value of k is plus 2, it is 2 omega naught. That is the second harmonic. When it is plus 3, it is third harmonic. And the negative values, you know that when there is a positive frequency term, there will be a corresponding negative frequency term as well. That is actually the representation by this k value, negative values of k. So in this way, you are ultimately getting all the positive and the negative frequency components. Those are ultimately actually the harmonics. So that means that k is the indication of the frequency term or the harmonic. So people generally don't write omega naught again and again. That means omega naught, 2 omega naught, 3 omega naught. They don't write like this. This is the usual practice. They write the value of k. That will indicate. If you write k equals to plus 3, that will indicate that it represents 3 omega naught. That means the third harmonic frequency in terms of the frequency of the third harmonic frequency. So in this way, you can find out all the coefficient corresponding to different frequency components. Okay, so it is in general, this is, and please note, you cannot change the sign. This comes by definition. So you cannot change the sign, because sometimes it happens that in MCQ type of question, it is written like that an or ak, the formula, is equals to 1 by t naught integration t naught xt e to the power, one of the possible, there may be multiple options. So one of the possible options may be, like this is suppose one of the options. The second option may be, suppose plus jn omega naught t or jk omega naught t dt. And you can argue, sir, I can put the value of n plus as well as minus, then it is immaterial. Yes, it is immaterial, that is logical, but you cannot write that. You cannot say your second option is correct. You have to say your first option is correct, because you have to check where you are getting this definition or this formula. That option will be correct. If it is replaced by plus, then it is not correct as far as the definition is concerned. Whether ultimately it reduces to the same thing or not, that is immaterial here. So you have to follow the convention, you have to follow the definition. That any logic, any argument, counter argument is not going to work. Are you getting the point? So this kind of question actually sometimes it is given only to test whether you know the definition correctly or not. So just look at here. I'm going to emphasize this thing, this term, this negative term, negative sign, j minus j k omega naught t. Here you have to write minus. No other alternative. You cannot write plus. So the point is, you know the definition of a periodic signal. I have written several times, x equals to xt plus capital T, and you know that t naught is the minimum t, where omega naught is basically 2 pi by t naught. That means t naught equals to 2 pi by omega naught, and this can be represented like this. Now you just see. Now you just see the difference between these two. Rather, these two. Here it is written once again. So the difference between these two. This is the relation between xt and ak in this way. This is also the relation between ak and xt in this way, in a different way. These two relations, these two expressions, okay, together, they actually tells you the complete story about the Fourier series. Or you can say, people sometimes call it a complete statement. If anyone asks you, give complete statement of Fourier series, that is the answer. You have to write these two expressions. They will give you the complete story. Full. Why it is full? Because just to see. Now look at here. xt is the input. Suppose you have a system. What is the system? Whenever you give any periodic input, it will basically decompose into its components. So that means the system taking the input, working, doing something, doing some kind of processing. What kind of processing? It is basically doing the Fourier series. Simple language, you can say. It is doing the Fourier series. And it is decomposing the signal into its frequency components, and the output it is giving. Look at this signal. When you excite this system with this signal, these are the frequency components you are going to get. So it is giving an output. It's something like, just to think like that. Now the point is, in this way, if you think, then this is my input. And this is my output. This is my output. So basically what you are doing, you are trying to get the input in terms of the outputs. So when you add on, superimpose all those outputs, all the individual components, you are trying to, theoretically, but mathematically, minus input to plus into all the infinite components, you are going to add on. Ultimately, what you are trying to do, you are trying to get back the input. So that means from the output, you are trying to go to the input. So it is kind of, the synthesis in terms of the circuit analysis. It is kind of synthesis. So where the output is known, that means here AKs are known to you. In this, when you apply this equation or this relation, when the AKs are known to you, AKs are known, if my AKs are known, I will just go for the summation and I will get back the xt. Or if not exactly, or at least try to do the good approximation of the xt. So it's kind of synthesis in that way. I know output, from that I'm going to try to get back or try to approximate or try to capture the input, the nature of the input. Okay, but again, look at this. Here, your input is known. Your input is known, and if you just do this operation, you are going to get the output. AKs are basically the output of the system. So you are going to get the output. So this is called the analysis equation. And this is called the synthesis equation. So this analysis and synthesis, that means in both way you can go. From input to output, so xt is given, you can get AKs. And if AKs are given, you can get back xt. Okay, at least mathematically, it is possible. So both, one is the analysis equation and the synthesis equation. 1 marks question ashe, Fourier series analysis equation ta lekho. But শুধু এইটুকু বলা হয় synthesis equation ta lekho. So তোমাকে you have to understand which one is the synthesis and which one is the analysis equation. So and both together gives you the complete statement of Fourier series. So এখানে একটা জিনিস নোটিস করো, আরেকটা জিনিস নোটিস করো, সেটা হচ্ছে এই যে যখন analysis equationটা হচ্ছে তখন basically you are doing the integration over a continuous variable time. T is basically a continuous variable time you are doing, and what you are getting some number, some discrete thing, AKs for different values of k equals to 0, 1, 2, 3. Okay, +1, -1, +2, -1, so on and so forth. But all the values, these are the values, these are the integer values. For that, you are getting some AK, some lines. It is just like a discrete time case, but it is not in time, it is in frequency. AKs are discrete, but not in time, they're in frequency. So it is basically time to frequency domain conversion. Because ultimately, when you are doing the integration over time, the concept of T actually lost, vanishes. T cannot be there, no longer. So what comes is basically the omega, actually K omega. So this way you can say the AKs are basically the representation in the frequency domain. As I mentioned, K equals to 1 means omega naught, K equals to 2 means 2 omega naught, like that. And K equals to 0 means it's a DC value. Okay. So this is discrete. So what we are doing, we are integrating when it is the analysis part is concerned, or you can say the analysis equation is concerned, you are basically doing the integration over a continuous variable time, and you are getting at the output what is called the discrete variable thing, which is in the frequency domain. Just some lines, just some numbers you are getting. But on the contrary, if you do the synthesis equation, if from the synthesis perspective, so here you are basically adding some numbers, AK, you are basically adding. All these are the discrete things, AK, because that is why you are doing summation. Okay, so you are basically adding infinite numbers. And you are adding, and ultimately you are getting back a continuous signal in time domain. So this addition is in frequency domain. It is in the frequency domain because look at the index or the variable, which is K, that represents the frequency component. So you are adding, that means ideally infinite number of frequency components you are adding. And by adding, you are ultimately trying to get back your original signal in the time domain, which is original signal with continuous signal in time. Okay, so these are the few things that you have to observe minutely. This is very important. Okay, now, so
So then it means that AK defines in the frequency domain, right? Like the K term is in the frequency domain.
Yes, the K terms is in the frequency domain.
Yes.
AKs are basically representing your frequency components. Okay.
That's why when we are adding in continuously, we are getting a continuous time signal XT, like in the time domain.
Yes. So they are the coefficient of this each and every frequency component. They're the coefficient, because look at this expression, you are multiplying this with the AK. So they are basically the coefficient. When you go for the plotting, when you go for, in the Fourier series I was discussing in one of the slides, it was there. If you draw the spectrum, you have to, what you do? You basically plot these AKs, no? These AKs. So either you plot the mod of AKs, that is called the magnitude plot with respect to K, because ultimately K is the frequency terms, okay, or the indication of the frequency terms. So you plot this is called the amplitude spectrum, or rather magnitude spectrum if you take the mod. And when you go for the phase, that is another part, that is the phase spectrum, that is the angle of AK, you plot, and that is also again with respect to K. So in general, you can say that AKs are basically the plot of the AKs, actually, whether it is the magnitude or the angle, that is with respect to K, will give you the spectrum, or the Fourier spectrum. And that is adequate to describe any periodic signal in the frequency domain. Okay, so different frequency terms, frequency components multiplied with AK is actually the coefficient. So Fourier coefficient. So that is multiplied, and if you keep on adding, the example, the graphical example I was showing in the last class, that is a blue colored square wave, and we are trying to replicate that with the help of superposition of different frequency components. Okay, first, second, third, fourth, like that. We basically kept on adding and trying to approximate, or trying to come closer and closer to this XT. But we cannot. That is different thing. So that is the thing. That is the synthesis. We are trying to synthesize that signal. with the help of some continuously time varying signal frequency component having different frequency values. So suppose okay, let's take one example. I think that will be clear. Suppose you have a very simple example. Start with a very simple example. Suppose you have this signal 1 plus cos omega naught t, cos omega naught t. Now if this is given, this is suppose xt. If this is given, now you may be asked to find out what are the values of the frequency Fourier coefficient for this periodic signal 1 plus cos omega naught t. Now of course the a naught, that means the DC part, just by inspection you can say it is 1. A of minus 1, because you know cos omega naught t can be represented in terms of e to the power minus j omega naught t divided by 2 plus e to the power plus j omega naught t divided by 2. So that means minus 1. Minus 1 means k equals to minus 1. A of minus 1 means for k equals to minus 1, the value of ak. So a of minus 1 is equals to, from here you can say it is half. Similarly, you know, if it is half, then just you can blindly say that a of plus 1 will also be half, because one will be the complex conjugate of other, and it's a real number, so it will be exactly this, half. So these are the three components you are going to get from this signal. Fine. Now if you have been asked to plot, as I mentioned, the plot of mod ak, that is the magnitude plot, and the phase plot, okay, this will give you a discrete plot in the frequency domain. This is not a continuous plot, this is a discrete plot, because as I mentioned, these are the few discrete values, but the discrete values in the frequency domain. Okay, so the plot will give you something like this. It's very simple thing. K. So suppose I'm going to plot AK, mod of AK. That means the magnitude, suppose. Okay, this is called the magnitude spectrum. So at 0, plus 1, minus 1, plus 2, minus 2, and so on and so forth. Okay, there are different discrete points. So for each and every discrete point, you have a value, you have a line on that. So here k is like an index, like n in our discrete time is a time index. Here k is a frequency index. Okay, it indicates the value of the frequency count, the frequency value actually. So here at 0, at k equals to 0, what is the value? The value is 1. So at k equals to 0, the value is 1. The frequency component whose magnitude is 1. It is a DC part actually. At k equals to plus 1, you have the positive frequency component, that is the first harmonic, positive. So plus 1 ki ache half. So it is somewhere here. So draw a line, half. At minus 1, it is also half. So here it is like that. 1 plus half plus half for both the sides. Okay, so this is the magnitude spectrum, because I have taken mod, so it is the magnitude spectrum. This is the magnitude spectrum in the frequency domain. This is magnitude spectrum. Now, if I have been asked to plot the phase spectrum, then again it will be plot of angle of AK with respect to K. Again, this will be the discrete plots, of course. There are different points, different index, 0, plus 1, plus 2, minus 1, minus 2, and so on. So as far as this phase spectrum is concerned, you just see all the values of AKs, all the values of the AKs are actually real positive number. So if they are real positive number, you know the phase is going to be 0. So the phase, if you have to plot the phase, then for this corresponding to this, it will be 0, corresponding to this, it will be 0, corresponding to this, it will be 0, and rest of the terms actually no longer actually do not exist. So I am not writing like that or drawing anything on that. So remember one thing, that AKs exist only for discrete integer values of k. You just look at the magnitude plot as well as the phase plot, a spectrum. It is basically for the discrete integer values of k is an integer number. It's the frequency index. And AKs exist only for those numbers. It is not a continuum thing. It is not a continuous thing. Okay. So as I mentioned, it's the integer multiple of omega naught. Omega naught is a particular value. It's a fundamental frequency. And if you multiply, it's an integer multiple, multiply by 1, 2, 3, 4, plus 1, plus 2, minus 1, minus 2, etc., etc. So those multiplicative factors are actually this k. So that means that is an indication of the frequency component. So it is in that sense, it's a discrete plot. So the Fourier series actually gives you a discrete plot in the frequency domain. Though the signal in the time domain is a continuous thing, but its plots in the frequency domain is a discrete. Okay, this is the point you have to understand. Okay, now I can do another example in this particular context. I can take another example rather. You can write xt like this way: cos 2 pi t plus half sine 2 pi t plus 1 by 4 cos 4 pi t. Okay, and the fundamental frequency is omega naught, say, which is equals to suppose 2 pi. So that means your t naught equals to 1. This is given. Okay, so this is 2 pi t half sine 2 pi t plus 1 by 4 cos 4 pi t. This is given. Now, just your next task would be to represent all these sine and cosine terms. Here, there is no DC term. So obviously, your A of 0, that means the coefficient, Fourier coefficient for a DC term would be 0 in this example. And you have basically three different components, three different terms, xt, cos 2 pi t, sine 2 pi t, cos 4 pi t. So for each term, you will get two different frequency components. If you represent it in exponentials, complex exponential form, so you can expect that how many AKs you can expect? How many AKs? A naught is 0. A naught is 0. That we have understood. And rest, how many AKs you can expect from here?
With A naught total 7.
With A naught total 7. আমি যদি বলি with A naught total 5.
হ্যাঁ স্যার the 2 pi to ওটা ডবল আছে হ্যাঁ স্যার
এক্স্যাক্টলি এটা দেখো খেয়াল করো ঠিক আছে cos 2 pi t sin 2 pi t তো ফ্রিকোয়েন্সি কম্পোনেন্ট একই আছে একটা শুধু কোসাইন একটা সাইন আর এখানে হাফ মাল্টিপ্লাই করা আছে সো বেসিক্যালি তুমি যদি রিপ্রেজেন্ট করো তুমি রিপ্রেজেন্ট করলে বেসিক্যালি কি পাবে তুমি করে দেখো a 0 তো 0 পেলে a অফ -1 টা কত পাচ্ছ বলো দেখি কেউ একটা a অফ -1 টা কত পাচ্ছ তার কমপ্লেক্স কনজুগেটটা হবে a অফ +1 যে কোনো একটা অথবা a অফ +1 টা বের করে বলো a অফ -1 টা কত ইটস লাইক দ্যাট তো ফুরিয়ার স্পেকট্রামকে আমরা বলি লাইন স্পেকট্রাম। আমি আমার একটা স্লাইডে তোমাকে দেখিয়েছিলাম আগের দিন তার আগের দিন। তো এটাকে বলে যে লাইন স্পেকট্রাম, বা এটা যখন আমরা রিপ্রেজেন্ট করছি এটা হচ্ছে ডাবল সাইডেড, দুটো সাইডে স্পেকট্রামটা আমরা দেখাচ্ছি, one for the positive values and another for the negative values. ঠিক আছে, ডাবল সাইডেড স্পেকট্রাম, because ultimately we are converting all the trigonometric form or terms to its equivalent exponential terms. সেই জন্য আমরা ডাবল সাইডেড পাচ্ছি। আর তুমি যদি সিঙ্গেল সাইডেড ডাইরেক্টলি করতে চাও তাহলে তুমি সিঙ্গেল সাইডেড পাবে। সো বেসিক্যালি সেটা ডাবল সাইডেড হোক বা সিঙ্গেল সাইডেড ডাজন্ট ম্যাটার, দ্য পয়েন্ট ইজ ইউ আর বেসিক্যালি গেটিং সাম লাইন স্পেকট্রাম, সাম লাইনস at different values for different values of k. So that is why in general it is called the line spectrum also. Okay, yeah, follow.
a -1 a +1 to 0 হবে?
a -1 a +1 0 হবে কেন? -1 মানে +1 মানে কি? +1 মানে corresponding to omega naught, where omega naught is 2 pi. K equals to 1 না? K equals to 1 তো। একটা তো এখান থেকে দেখি বলা যাচ্ছে হাফ হবে ফার্স্ট টার্ম,
+1/4j হাফ -1/4।
এক্স্যাক্টলি হাফ প্লাস 1/4j হাফ মাইনাস এর কমপ্লেক্স কনজুগেট 4j। আর এটা তো খুব ইজি, a of -2 and a of +2, it will be just equals to 1/8। 1/8 এই পাঁচটা দেখো 1 2 3 4 5 ইনক্লুডিং a naught, ঠিক আছে। সো a naught টা ইন বিটুইন থাকছে, সো ইউ হ্যাভ টু পুট দ্যাট 0। ওকে, সো তোমাকে 0 থেকে দেখাতে হবে। যাই হোক, সো এই পাঁচটা তুমি লাইন পাবে, সো ইউ উইল গেট 5 লাইনস ইন দ্য স্পেকট্রাম which you have to plot. এবারে তোমার এটা হচ্ছে ম্যাথমেটিক্যাল এক্সপ্রেশন বলতে পারো, ঠিক আছে, হাউ ইউ আর রিপ্রেজেন্টিং ডিফারেন্ট ফুরিয়ার কোএফিশিয়েন্ট ম্যাথমেটিক্যালি for this particular case. Now it's corresponding, এবারে তুমি একে it corresponding amplitude, মানে if first you have to take the mod, then you can plot the amplitude, and you have to take the angle, then you can plot the phase. So in this way you can plot the amplitude spectrum as well as phase spectrum. যেমন আমি যদি লাস্ট দুটো, if we consider these two, what will be the phase? Both are positive number, so positive integers, positive number. So আমি যদি নি ফেজ নিয়ে ক্যালকুলেট করি আমি কি পাবো? দুটোর ক্ষেত্রে 0 পাবো, ঠিক আছে। if I calculate this for these two terms, a of -1 and a of +1, if I calculate the phase, what phase I will get? Phase কি করে ক্যালকুলেট করে? অ্যাঙ্গেলটা tan ইনভার্স
-1/4/1/2 আর কি।
হ্যাঁ, তাহলে প্রথমটার এটার ক্ষেত্রে ফেজ কত হবে বলো? এইটার ক্ষেত্রে a of +1 এর ক্ষেত্রে অ্যাঙ্গেলটা কত হবে? এরকম ভাবে যদি বলি আমি a of +1, এইভাবে যদি লিখি, ঠিক আছে, অ্যাঙ্গেল এইভাবে, it would be, and this case
tan inverse half আর tan inverse -half।
ওকে, আমি এইভাবে লিখছি তাহলে, ঠিক আছে। আর এটা প্লাস হবে তাহলে, তাই তো?
উল্টো হলো মনে হচ্ছে।
কেন? tan ইনভার্স -b/a না?
হ্যাঁ স্যার।
তাহলে এটা কি আছে দেখো, ভুল লিখলাম? সবাই দেখো, চেক করো, যদি ভুল হয় বলো। দাঁড়াও আমি বলছি, এখানে জেবি যখন ওপর নিচে মাল্টিপ্লাই কি হবে, টার্মটা কি থাকে, এ প্লাস জেবি, তাই তো? ট্যান ইনভার্স এই মাইনাস হয় না তো, প্লাস হয় তো মনে হয়।
না স্যার, প্লাস হয়।
হ্যাঁ হ্যাঁ সরি, প্লাস হয়, বি বাই এ হয়, তাই তো? এটা তো, এটা হয়তো ট্যান ইনভার্স বি বাই এ, হ্যাঁ তাহলে তো ঠিকই আছে, ঠিকই আছে। এটা যখন জে দিয়ে মাল্টিপ্লাই করবে, ওপরে জে থাকবে, নিচে জে স্কয়ার, এটা প্লাস হয়ে যাবে না? সো প্লাস হয়ে গেলে ট্যান ইনভার্স কি হবে, হাফই তো হবে, আর এটা মাইনাস হবে। ঠিক আছে, ঠিকই লিখেছি। সো -1 এরটার জন্য হচ্ছে প্লাস। দেখো মানে মোটা কথা হচ্ছে এটা একটা অড ফাংশন, ফেজটা হচ্ছে অড ফাংশন, আর এটা অ্যামপ্লিটিউডটা হচ্ছে বেসিক্যালি, আর ম্যাগনিটিউড যাই বলো, তো ম্যাগনিটিউড নিলে তো অবশ্য ইয়ে হবে, সবই পজিটিভ হবে, বাট এনিওয়ে ইন জেনারেল তুমি যদি দেখো, ইট ইজ বেসিক্যালি an even function, ইট ইজ বেসিক্যালি an even function। তো সেটাই আমাদের স্লাইডে ছিল, যে আমরা দেখিয়েছিলাম ইন দ্যাট স্লাইড, ইট ওয়াজ দেয়ার that magnitude plot will be an even function and phase plot will be an odd function। দেখো সেটাই পাচ্ছি from this example also। ঠিক আছে, আচ্ছা আরেকটা কথা একটু মাথায় রাখবে, যে যদি ধরো এখানে তো এক এর যে ভ্যালুগুলো আমরা লাস্ট এক্সাম্পল এবং ইন দিস এক্সাম্পল অলসো, what we get all are basically some positive real number, some positive real number we are getting, like in this case 1/8. In the last example I think it was half, okay, some plus half, here it is plus 1/8. So the corresponding phases are 0. But if suppose the number is real, but suppose this is negative, in that case your amplitude will be same. Suppose if instead of 1/8, if it would have been 1 minus 1/8, suppose, then in that case the amplitude plot will be same. There will be no change in the amplitude plot. But the phase, as far as the phase is concerned, it will be কি হবে, it will কি হতো বলো তো, ফেজটা কি হতো, 0 থাকতো কি? যদি নেগেটিভ রিয়েল নাম্বার হতো তাহলে ফেজ কি হতো? ফেজ পাই হতো, ঠিক আছে, ফেজ হতো পাই, অ্যাঙ্গেলটা হতো পাই। এবারে পয়েন্ট হচ্ছে, ইউ হ্যাভ টু আন্ডারস্ট্যান্ড দ্যাট you know that your phase is basically a odd function, basically an odd function. So it cannot be plus pi always, it can even be minus pi, it doesn't matter. So when you have a real quantity which is negative, a real number which is negative, it is not that the phase will always be plus pi. The phase can be negative pi also, it can be plus pi, it can be minus pi. But you have to understand that, as you know that from your experience, you know that your phase plot will be an odd function. So if it is an odd function, then of course if at one side, or for one side means suppose the positive values of k, if you go for positive angle, of course for the negative values of k you have to go for the negative angle, or the vice versa, or in the other way around. If for the positive values of k with the positive side, if you plot the negative angle, then at the negative side you have to plot the positive angle. That means there can be different types of phase plotting, different possibilities are there, so as to capture the information that your phase plot would be an odd function. That is the point, and what I'm trying to say. Okay, but another thing is that even though your it is actually in terms of the phasor, you can say, if you have a phasor plot, suppose you, as you know, you can move in this way, in the anti-clockwise direction, or you can move in the clockwise direction as well, as this way, like this. So ultimately you are going from 0 to pi. So the source and the destination are same. Source and the destination are same, but the point is which path you are following. Which path you are following. If you move along this direction, That means your angle will be positive. So it will be positive pi. If you move along this direction, that means the clockwise direction, your angle will be negative. Okay. So ultimately, it actually indicates, the sign actually indicates with which path you are following. So that is the point. Yeah. Otherwise, the source and the destination are basically same. So ultimately, we are reaching at the same point, but which path you are following to reach there. So anyway, okay, let's take another example. I think then the thing will be even be clear. Okay, so look at this. So this is a signal. It is a xt. It's a periodic signal, periodic rectangular pulse, or sometimes people call it train of pulses. So here the width of the pulse is 2t1, extending from minus t1 to plus t1, and it's an it's an even function. So minus t1 to plus t1, this is the width. So width is basically t1 minus of minus 2, it's 2t1. It's the width of the signal pulse, sorry. And the period is from this point to that point. So obviously the period is t0. So this is mathematically defined like this: xt equals to 1 mod t less than t1. So as you can understand, and 0 t1 to t0 by 2 for both the sides, positive as well as negative. That is why mod sign is taken. So this is the definition, and this is its pictorial form or depiction. So again, the question is same. You have to first find out the AKs, calculate the AKs, and from that you have to go for the plotting of its magnitude and or amplitude or phase spectrum. Okay, the Fourier spectrum in general, you can say Fourier spectrum jodi kotha ta bola thake, that means you have to plot both magnitude as well as phase. But if it is specifically written that you plot this magnitude or particularly plot phase, then you just do that. Okay. The term গুলো একটু মনে রাখবে, অনেকে বলে লাইন স্পেকট্রাম, ঠিক আছে? লাইন স্পেকট্রাম মানে এগুলো বিভিন্ন রকমের টার্ম, বিভিন্ন রকমের ওয়ার্ড ইউজ করা হয়, ব্যাপারটা একই। যাই হোক, এটা করো চটপট। যে এরকম একটা সিগন্যাল আছে যেটা বললাম, এইভাবে ডিফাইন করা আছে ম্যাথমেটিক্যালি, পিক্টোরিয়ালি ছবিও আঁকা আছে। তো এর ক্ষেত্রে তুমি বের করো এক্স এ কে ভ্যালু গুলো বের করো। So xt is given, you have to find out ak. Just you go for the integration. Integrate করো over a single time period. করলে কি পাওয়া যাচ্ছে বলো? একের ফর্মটা কি আসছে? one by t naught integration over one time period xt e to the power minus j k omega naught t dt. এই তো এক্সপ্রেশন। এবারে এই পার্টিকুলার কনটেক্সটে এই এক্সাম্পলটা রেসপেক্ট কত আসছে? সরি, a naught তো এখান থেকে দেখেই বলা যায় a naught is basically the average, and dc তো basically the average। তো একটা সিঙ্গেল টাইম পিরিয়ডের উপর যে অ্যাভারেজ করো সেটাই হচ্ছে বেসিক্যালি ডিসি। তো এটা তো মুখে মুখে বলা যায়, এর জন্য ইন্টিগ্রেশনও করতে হয় না। কত হবে অ্যাভারেজ? এটা হচ্ছে 2t1 into 1 area under the curve divided by this period. তাহলে কত হলো? 2t1 into 1 area under this এর এরিয়াটা পেলে divided by t0. এই তো মুখে মুখে বলা যাচ্ছে। So 2t1 divided by t0. This is a0. For rest of the case, you have to do the calculation. Just after doing the integration, what expression you are getting? Just tell me.
So is it minus j omega e to the power?
দাঁড়াও ak equals to বলো
Minus j omega naught
minus j omega naught
e to the power minus j omega naught t1 minus t.
হ্যাঁ t1 কোথায় পেলে? ও 81 মানে এটা বলছো? 81 এইটা?
হ্যাঁ স্যার।
আচ্ছা আবার বলো, কি বললে আবার বলো?
না স্যার, এক মিনিট দাঁড়ান, ক্যালকুলেশন মিস্টেক।
এই t0টা তো মাইনাস t1 টু t2 হবে, মাইনাস t1 টু প্লাস t1 হবে ইন্টিগ্রেশন যখন করি, আর এই x এর ভ্যালুটা হয়ে যাবে 1। এই তো ইন্টিগ্রেশন। এটা করলে কি পাচ্ছ? xt তো 1 আছে, xt is 1,
তো মাইনাস j omega naught
minus j omega naught
divided by t naught
divided by t naught, okay,
e to the power minus j omega naught 2t1
j omega naught 2t1 এটা?
হ্যাঁ স্যার।
সবাই তাই পাচ্ছ? সবাই কি তাই পাচ্ছ? এই কমপ্লেক্স এক্সপোনেনশিয়ালে একটাই টার্ম পাচ্ছ, আর কোনো টার্ম পাচ্ছ না? আচ্ছা বাকিরা কি বলছে? আরে তাড়াতাড়ি বলো, একটা ছোট্ট ইন্টিগ্রেশন করতে এতক্ষণ লাগলে তো মুশকিল।
So the integration will be 1 by t naught into in denominator.
Just a minute. 1 by
Yeah.
T naught. Okay.
Into 1 by minus j n omega. I mean here k you have used 1 by
1 by minus
minus j k omega naught.
jk omega naught. Okay.
Then within brackets we'll have e to the power minus j k omega naught t1
the power minus jk omega naught t1
minus e to the power plus j k omega naught t1.
Okay. Now, okay, let me remove this. Okay, you just look at this expression bit carefully and try to reduce it. There are
Sir,
two.
2 by jk omega naught t into sine k omega naught t1.
আবার বলো।
রিডিউস ফর্ম আর কি, যেটা স্যার
হ্যাঁ, ওটা কি হবে তাহলে আলটিমেটলি?
2 by k omega
2
naught
by k omega naught t বলে তো কিছু নেই, হয় t naught আছে বা t1 আছে।
t naught স্যার, t naught স্যার, মানে t মানে
t naught। আচ্ছা, এইখানটা আমি একটু তোমাকে একটু ইয়ে করছি। হ্যাঁ, এই যে k omega naught t1, can't you reduce it? k omega naught t, আচ্ছা, what is t naught? What is t naught?
Yeah, 2 pi by omega.
Yeah, exactly.
Yes.
তাহলে then
Yeah, and 2 will cancel and we'll have
2
1 by
will
2 pi.
cancel. Very good. And it will be reduced to 1 by k pi. Very good. And then multiplied with sine
k omega t1.
k omega naught. Omega naught
Yes.
t1. This is the term you are getting. Okay, this is the final form. You are getting it. And now our job would be to represent this even in better form, in better way. That means the way we know this function actually. So this representation would be, you know the function sin x by x. Sin x by x, this function. Sinc function, people call it. Sinc function, sin x by x. So our objective is to represent this in this form, in this term. That means the form of the term which is known to us, which is we are familiar with already. Okay, so for that, what we are trying to do? For that, let me remove this portion. Okay, just to see that I have this sine k omega naught t1 divided by k pi. So that can be written as, so from here, I'm coming here. So what is the argument? This argument is k omega naught t1. And here it is k into pi. But I have to write it like sin x by x. Sin x by x. So of course, sine within bracket k omega naught t1 divided by, at the denominator I have to write like this, k omega naught t1. So here I have k pi. So automatically I have to, here it will be pi, and at the numerator it will be k, I'm sorry, not k, it will be omega naught into t1. Okay, so this is the way we have represented this thing, because then this can be written as sinc function. Sinc of your, that means what I'm trying to say, it is actually equals to omega naught t1 divided by pi into sinc, S-I-N-C, sinc of say phi, where phi is equals to k omega naught t1. So it's a better way to represent. So that we have represented in such a, or in the term or in the form of sinc function, so that the form is known to us. We can deal with it properly, correctly. Okay. So now we just see, you know the definition of the sinc function, how to form that, etc. So তোমরা সবাই জানো তো? আমি তো হ্যাঁ নোন বলে দিচ্ছি. Everyone knows, I think. sinc function sin x by x form?
Yes, sir.
সবাই জানো? যদি যদি কেউ না জানো বলতে পারো, মানে হেজিটেশনের কোনো কারণ নেই।
আপনি একবার বলে দিন।
আচ্ছা, আমি একবার বলে দেবো, ঠিক আছে। তাহলে আমার কাছে একটা স্লাইড আছে, আমি সেই স্লাইডটার হেল্প নিয়ে বলি তোমাদের।
হ্যাঁ স্যার।
এই দেখো, দেখো, it is the form of a sinc function sin x by x. It is a very, very beautiful function actually. If you integrate sin x by x, you know that sin x by x can even be written as a Dirac delta. So Dirac delta is a specific case because there are different functions which can be written in the forms of delta, or you can say the Dirac delta function can be written in the form of that function, whether that is a rectangular function or a triangular function or a sinc function, and for as a special case of that. But anyway, this is another function, a sin x by. If you integrate this function, okay, it is actually an even function. If you integrate that function, so this is actually gives you the value which is pi. The area under this function is actually pi, and this integration is not very simple. There is a special types of, there are different methods. So anyway, so I'm not going into that. So the point is, this type of function, this sinc function sin x by x, okay, this is in, as it is written in signal processing, you will encounter every now and then, almost very often you will encounter this function. So whether in the signal processing or image processing or any kind of communication related things, you will encounter this kind of function very often. Okay, now how to understand? You can understand this with basically there is a multiplication of two functions, sin x and 1 by x. But individually, you know, you can plot sin x easily and you can plot 1 by x. Now if you plot sin x and 1 by x individually, then obviously if you just multiply these two, you can plot sin x by x. Not a big deal. So just to see, it is basically, you know, that from the childhood days you are doing the application of as an application of limit. You know, the sin x by x, when x tends to 0, you know that this is basically 0 by 0 form, and there you apply the L'Hospital rule and you get back that cos x by 1, when put x equals to 0, it will give you 1. So you know that sinc function when x equals to 0 or tends to 0 rather, not equals to, or approaches 0, then it gives you 1. That we understood. So sinc 0 is 1. That we know from this, from our actually knowledge, past knowledge, previous knowledge. So we know that. And the point is, actually when you this, we also know that the maximum value of sin x is +1 and the minimum is -1. So sin x always oscillate between +1 and -1. That is also known to us. Again, we know from our previous experience, we know that, or knowledge. So I can write like this. This relation can be written like this. It is in between -1 and +1. It cannot go outside within this range, always within this range. Now if we divide by x, then it will be -1 by x, sin x by x, and less than equals to +1 by x. So that means what? That means this function always moves between this and this. And look at this. This is in its own 1 by x is basically nothing but your actually rectangular hyperbola. So it is providing you kind of a damped nature as you increase the values of t. So basically it will give you a damped nature. So it is asymptotically approaching to 0. And if x approaches to 0, then it suddenly blows up and almost asymptotically approaches to infinity. So this is the peculiar nature of this function. And now you just understood that the sin x by x actually the ranges between this -1 by x and +1 by x within this. So in this way, it is pictorially depicted. Look at this. This actually represents this blue card 1 by x function. When x is positive, it is something like, when x is negative, it is like this. Similarly, -1 by x also the same thing. You can write like, draw like this. And with it, this is the limit. This is the boundary we are putting in all for the all 4 quarters. We are putting the boundary. And this green color signal is basically the original sign x, the original sign signal, which is varying from minus infinity to plus infinity for all values of x. And now we have understood that this sin x by x, actually that means a sinc function, is limited or bounded in between this. So these are the boundaries. We are just first drawing the boundaries and trying to damp it, forcefully restrict this green signal, which is supposed to move like this, but we are forcefully restricting within this. And it is actually indicating a damp nature, as I mentioned. It is asymptotically approaching to 0 for both the sides. But here it is asymptotically approaching to infinity. But the point is, here we have understood that it cannot go up to infinity because it is bound to be 1. So only at 0 value it is 1. For rest of the values, or for the other values of x's, it will be bounded by this limit, minus 1 by x to plus 1 by x. So if you just do it, so the resultant curve will look like this. This is the black one. It's like this. And it is actually an even function. So at this point, this function will provide you the maximum value, and that is equals to 1. And if you take the area under this curve, you will get minus infinity to plus infinity, you will get pi. And half of this is equals to pi by 2, as it is an even function. So from 0 to plus infinity, if you can find out the area, you just multiply by 2, then pi by 2 into 2 will be pi. So the total area would be pi. It's a very, very unique function. And it is kind of a damped sinusoid. It is oscillatory. It is oscillated because it actually crosses and goes for the negative values, and again crosses the axis and go for the positive value. And this way it basically moves up and down, up and down, up and down. But it amplitudes decays with x. That means or if you plot in terms of time, I would say with time it starts decays. So it's kind of a damped oscillation, kind of. It's this oscillatory nature. You are actually getting the nature of the sine wave, but which is damped. That is, amplitudes are not constant. Amplitudes are not fixed for each of the oscillations. So that is actually going to decrease with time or x or whatever you say. That is the independent variable. Okay. So this is how the function actually looks like. That is black one. So okay, this is actually another thing. No, I will not show it at this stage. I will show it later. So understood. This is actually sin x by x. So if we understand the nature of the sin x by x, so the point is here, you just see. So in general, the expression of AK, expression A, this one, AK, the expression of AK from the expression of AK, sorry. The conclusion we can make is that this is actually a real number. All the AKs are real because it is sin x by x. So sin is a real function. So sin x by x form. So it is actually a real number, a real thing. That means what? That means that phase is either will be 0 when the number will be positive, because sin x by x, it has a positive value as well as negative value. So real number, but maybe positive, maybe negative. For some cases it will be positive, for some cases it will be negative. So when it is positive, the phase will bound to be 0. But when it is negative, the phase may be minus pi or maybe plus pi. So this is the point we have understood. Now our task is to plot it. And we also know that in this case, it will be a discrete plot. It will be a line spectrum, because in the argument is not a continuous variable like x or t. It is a discrete thing. Why? For k equals to 1, it will be omega naught t1. For k equals to 2, it will be 2 omega naught t1. For k equals to 3, it will be 3 omega naught t1, and so on and so forth. So it will be basically a discrete plot. It will be a spectrum, line spectrum. Some lines will be there, but if you just connect the tips of the lines, that is the envelope that you are supposed to get, will look like a sinc function. That means sin x by x. Sin x by x means this. Oscillatory, but it's kind of a damped oscillation. Oscillatory nature, in both the side, but it can be damped oscillation, but it's an even function. So this kind of nature. So that when you this tips, if you connect it, it will look like this sinc function. It will look like this sinc function. So it is a damped nature. You just see, if you just connect these amplitudes, it will be like a damped oscillation kind of. In this case, what would happen? In this case, basically, we are going to get the envelope will look like a sinc function. That means what I'm trying to say. Okay, let me plot it. I think that will be better. So suppose if it is K, it's a relative plot. Obviously, I don't have the exact values. That means the values of these T1, T0, the numerical values I'm talking about. So then it will be easy for me to plot, go for the exact plotting. But here I'm just trying to give you a sense. It is AK. Suppose it's an amplitude plot. Amplitude. I mean, may have the positive value, may have the negative value, etc. So I know that when K is 0, A of 0, that I'm talking about, A of 0. What will be the value of A of 0? A of 0 here, sin x by x will give you 1 for K equals to 0 or for x equals to 0. So, and that is multiplied by 2t1 by t0. So, of course, here it will be 2t1 by t0. This is the highest value, maximum value I will give at for K equals to 0. And always remember this form, 2t1 by t0. Well, what is t1? T1 is actually the half of the width. Width is 2t1. So t1 is actually half of the width. Or in other words, you can say the numerator will be 2t1. That means 2t1 means the total width of this pulse. That means whatever the pulse will be given, you just check or verify what is the width of that pulse. Whatever will be the width of the pulse, you just write it in the numerator for the DC term. And the denominator, in the denominator, you have to divide it by the T0. Now, what is T0? T0 is basically the period. So simple to remember. Any kind of pulse, if it is given to you, you can, without doing any mathematics, you can straightforward write this thing. That is 2t1 by t0, where 2t1 is basically the width of the pulse and t0 is basically the period of this periodic signal. So just to divide these two, and you will get the actual spectrum, or sorry, the A of 0, that is the one of the spectrum. So that is for K equals to 0. That is the DC term you will get. Now again, after that, immediate term for another, that's the discrete plot. So again, I have to draw another line. It will be better if I first draw the envelope. And I know how the envelope would look like. The envelope will look like a sinc function. Look at, I am not drawing a continuous line. I am drawing a dotted line. I am drawing a dotted line because it is not a continuous function. It is a discrete function. It's like this. The point is just to see, as I mentioned, it's an even function. So now what you have to do, you have to draw some lines for different values of K. It is 0, it may be 1, plus 1, it may be minus 1, it may be plus 2, it may be minus 2, and so on and so forth. So the number of lines within this lobe, this is called lobe or null. This is the first lobe, this hump. Whatever is there within this hump, it is called the first lobe or first null, NU. Okay, in EM theory, you have heard the term lobe or null. This kind of terms you are already familiar with. So this is on the second null or second lobe. This second hump. Okay, this is called the third lobe or third hump or third null. Okay, now again, there is a crossing point where it actually crosses, because you know in the sinc functions you have some positive values as well as negative values. The negative values, that means for the negative values there will be some lines, just like this. And this slope, because whatever is there for the positive values of k, the same thing will be there for the negative value. That means that will be replicated, kind of. It will be replicated, it will be identical. So here also, there are, if suppose there are 1, 2, 3, 4, 5 lines within this, then obviously here also there will be 5 lines, each having the same value. Okay, so these two will be identical. Similarly, these two will be identical. If suppose there is 4 lines, suppose Acha, line. Here also there will be 5 lines. In this way, it will basically go on. Now, this is called the amplitude spectrum. Amplitude spectrum. This is because you have the positive values of k, AKs, negative values of AKs, etc. An envelope looks like a sin x by x. Okay. Now, if anyone asks you to plot the magnitude spectrum instead of amplitude, if it is asked that you have to plot the magnitude spectrum, then you know what to do. You have to take the mod. Mod means all the negative values will go up. So that means suppose I'm drawing one for you. You just remove this, and then it will be kind of this. Everything will be positive. Here also, it will be positive. It will be positive, like that. All the humps will be positive. You have to plot it in a positive direction. Okay, so it is called the magnitude spectrum, and it's, look at this, it's an even function. It's an even function. Okay, and also another point to note, that most of the power, because yesterday we discussed about we introduced actually the Parseval's theorem or Parseval's relation. In Parseval's relation, we have seen how the energy is related for the time domain and the frequency domain. So in the time domain, you have a signal which is a periodic in nature. You can find out its energy over one time period. In the frequency domain, suppose in case of Fourier series, when you are decomposing into a number of sinusoids, and for each and every sinusoid, you just find out its energy and just add on all the energies. You will actually get back the energy of the original signal. So here, what you are doing, you are basically drawing the components of the frequency components. That means suppose for k equals to 1, k equals to +2, +3, +4, plus etc. Likewise minus. And for each of the components, this value, this amplitude, actually giving you its square will give you the energy for that component. And if you add on all this, you will get actually the energy of the total signal, original signal, xt. xt means this one over a single time period. Now the point is, if you calculate, I have an example I will give you, and you will just, as an homework, you will do it. So you can find out that 90% of the energy or the power is actually hidden within this first law. 90%, just to think. That means you have this signal, whatever energy of the power of this signal has. So actually it's a periodic signal, so you know that actually the concept of energy in that sense is not applicable unless you do it for a single time period. But anyway, if you think from the perspective of power even, that is also okay. So then also the 90% of power is actually hidden within this first law. That means you don't need to bother, and the reason is very simple. Look at the heights. Look at the heights of this your AKs. I mean these harmonics. Look at the heights; they're very smaller in comparison to this. In comparison to the AKs, which is there in the first lobe null or first lobe, the other AKs in the other nulls or other lobes, they're smaller, much smaller. And as a result, obviously the energy amplitude square is the intensity of the energy, you know. So of course that will be smaller, that will be much smaller. So that is why the typical calculation will show you that 90% of the power is basically hidden within this. So now if we can design a filter, suppose if we can design a filter which can pass only this null and block all other null, rest of the nulls, so that is good enough. This is one of the applications I'm talking about in the perspective of this example. So this filter, suppose within this range, if it can passes only this first null and blocks all other null, that is good enough, because 90% power I'm getting. Rest 10% I don't bother. For rest 10%, there is no need of sending such a long signal. Okay, so that is the way. This is a design perspective, right? As a designer, as a communication engineer, you have to understand that our objective is to transfer the power from one end to another end. And in doing so, whatever will be my optimized way, the optimized means, I will follow that. I will not go blindly in sending all this big signal. That is it. That's all the frequency component. Why should I allow when I am getting 90% within this? This is one of the applications. In application, you will do it. As I mentioned in the slide, in signal processing, very often you will encounter this kind of signal. Very often. So there you have to understand that thing. So I'm going to give you an assignment and homework. Just a minute. Yes. No, this one. Yes. Yes, look at this. A rectangular pulse train. One particular pulse has been captured. It's a periodic thing, periodic signal. Now, here one particular period is considered. Okay, one particular period is considered within this. And this rectangular pulse having height 1, and this is the width, as you can see from here. Okay, so axis is given. It is in second. So the numerical values are given. It is in second. It is in volt. Okay. So this I'm not going to do that. I have already introduced the concept, and you will do it in your home. Okay. So this is what particular one period has been captured. Here, it's a periodic signal. One particular period is considered, and this is the width of the pulse, and this is the period of the pulse. And now, if you do the calculation, you will find out this thing. And look at this, only the first lobe has been shown. Only the first lobe has been shown. And here they have calculated different power corresponding to different frequency components. Look at here. The power corresponding to this 0th frequency, the d theta, it is the mod of f naught square. Power corresponding to the first means it is, you have 2 at the both sides of the spectrum, so obviously you have to multiply by 2. So this square multiplied by 2 for the first frequency, that means the first frequency component, first harmonic. Then it is a second harmonic, and again multiplied by 2. So 2 is taken common. So 2 into f2 square, 2 into f3 square, and so on and so forth. And this is the time period. It is given 0.3. Why it is 0.3? Because 0.15 in this side, and this side minus 0.15. So 0.15 plus 0.15, which is 0.3. And the period is given 0.05, because look at this. It is half of this 0.05, half of the 0.05. So when you add these two, it will be 0.05. So these two information, with the best of these two information, so you have to calculate the power or the average power. It's the average power is given here. And here, these are the power corresponding to or associated with each of the frequency components. Okay, in the spectrum. And if you just add on all these and you compare, that your power will be the 90%. The 90% of the power that just now I mentioned, that is contained within the first null. Within this first null, the power, first we calculate the power of this signal. what is given in the time domain. Then you go for this plot in the frequency domain and only restrict yourself within this first null. Only within the first null. And for each of the spectrum, you just calculate the power and just add on to get what is the power of this first null. And then compare this power, what is the percentage of this power, of this total power of this signal. And you will check that, you will verify that it will be approximately 90%. And from that, this conclusion can be drawn. So that's the very, very good example, and you just do it by your own, and it will help you. Anyway, so this is the the magnitude plot, and then we are interested in the phase plot. In the phase plot, what we'll do again, we will plot with respect to k, the angles we will plot. And just to see, for the first null, for the first lobe, everything is positive. Everything is positive. That's a positive real number. So obviously, if you plot angle of AK, it is bound to be 0 up to this range. All are 0. All are 0. Okay. Here it was negative. Here also it was negative. Actually. Okay. Negative. Now, when they are negative, as I mentioned, negative real number. So either they'll be plus pi or minus pi. Then, if you plot it like minus pi here, that is 5 lines. Okay, like this. Then again, it will be 0. Then, of course, to retain the odd nature or the odd property of the phase spectrum, you have to plot this in the positive direction, that means the positive pi. This. Or if anyone interested to plot it in the negative direction, positive direction, to get the positive pi, then this part will be plotted in the negative direction to have the value of minus pi. Or there may be some twisting also. That means one may be plus pi, another may be minus pi, another may be plus pi, minus pi. Means there may be multiple options, multiple possibilities to plot the phase spectrum. But in each and every possibility, you have to ensure that ultimately, overall, odd nature of the phase spectrum is retained or not. If it is retained, then it is okay. So you have to retain that property. Otherwise, it is okay. You can go for any options. You have multiple options, multiple possibilities you have, basically. So just remember this thing, because I have given a special attention on this particular type of problem, because as I mentioned, in different applications for the different courses yet to come for you, you will face this every now and then. So then it will be easy. If you are familiar, if you have a good familiarity with this, then it will be easy to deal with at those times. Okay. আচ্ছা, অলরেডি আমরা এখানে কতটা ডিসকাস করেছিলাম? আমরা তো ডিসকাস করছিলাম মেইনলি এই পার্টটা। আচ্ছা, আরেকটা পয়েন্ট এখানে নোট করার আছে যেটা আমি কালকে মেনশন করতে খেয়াল ছিল না। সাপোজ ইন জেনারেল আমরা অলরেডি এই পার্টটা অবধি ডিসকাস করেছিলাম, পার্সিভালস থিওরেম, ওকে, এন্ড দ্য ভেক্টর সিগন্যাল অ্যানালজি পার্সপেক্টিভ থেকে সেটা আমরা ডিসকাস করেছি। সো হিয়ার the point is, if the signal is in general complex, actually in general every signal is complex, so the result of that means whatever we have done so far, that is the integration, this one, the integration over this time period, we are basically defining an orthogonality of real signal x1, x2, x3, x4 up to xn. So any two signals you have taken from that set, orthogonal set, and you are multiplying and integrating over the time period t1 to t2, that period, what that is going to give you. Okay, that is the integration actually indicating. Here also we are doing the same thing. The only point is that we are dealing in general a complex signal. So while we deal with the complex signal, one signal is taken as it is, another signal is taken as its complex conjugate. So xmt and multiplied with the xn star, that is, it's the complex conjugate of xmt. You have to take that. And again, the same logic. So when m is equals to n, it will give you the energy, and when m is not equals to n, it will give you 0 value. And rest of the things are same as we have already did in the last case. But the point to note here is that here the Cn actually comes out in our previous case. The Cn actually comes out to be this 1 by n, the energy of this signal of the component xnt, this component signal. It is one of the components in that orthogonal set, and into integration from T1 to T2, that is within that interval of the range of interest, and integration over the original signal ft, which we are trying to approximate, multiplied with that component, that very component. Here also the same concept. The only thing will be it will be a complex conjugate of that. That is the only difference. Okay. But anyway, that is not a problem. This is mathematics. That is not a problem. It is okay. But the point to understand is that this note is very important. Very, very important. This note. It actually indicates that suppose you are going to add different terms. Just to see, you are going to add different terms. x1t, x2t, x3t, and so on and so forth. And each of the term is weighted by a factor, C1, C2, C3, C5, C6, etc. Which is nothing but in our Fourier concept, from Fourier perspective concept, or from that point of view, we can say it's a Fourier coefficient. Okay, so when we are adding the first signal or the first component, say, okay, that is a suppose C1 x1t. We have first introduced this thing. That means here in this example, in this example, suppose the first signal we have drawn to approximate C1 x1t. Okay. Now we have introduced the second term, the second component. Suppose C2 x2t, which we have added with this, and we got this resultant shape. That is, now in this case, in the second step, in this step of approximation, I have two signals. One is the first one, C1 x1t, and another is the second one, C2 x2t. Suppose. In the third step, I have added another component with the previously added two components. That is C3 x3t. Okay. In the fourth phase of approximation, even to make the approximation even better, we have added another component, that is suppose C4 x4t. In this way, we basically keep on adding and adding and adding terms one after another to try to approximate the signal in a much, much better way. Fine. Now the point is that when you are adding one particular component, suppose here this component, C3 xct, the other two components are not going to be impacted. When we are adding the second component, that is a C2 x2t, the other two components, the first component, that is the C1 x1t, here in this case, is not going to be impacted. So that means in general, we can draw the conclusion that Fourier coefficient, the Fourier coefficient that you are going to add is not going to impact the previously added Fourier coefficients. It's a very nice thing, very, very nice thing. So that property, here it is written, you just see that any coefficient in this process of approximation that you are adding, that you are using, okay, is not going to hamper or not going to disturb the previous terms or previously added terms, that means the other coefficients. And that is one of the advantages you can exploit in this Fourier synthesis. It is a synthesis, no? You are keep on adding the terms and superimposing one terms with other, and ultimately you are trying to get back your original signal xt. This is called this particular property or feature is called the finality values of the coefficient. That is very important. It's short question জিজ্ঞেস করে MCQ তে আসে অনেক সময় ভাইভাতে জিজ্ঞেস করে. So finality values property of the finality of the values of the coefficient. That is, the whatever value you have added, it's the final. That is not going to change, even though you are going to add some terms in future. That is the final. That means once C1 is used in association with x1, that coefficient is fixed. If you add C2, if you add C3, C4, C1, even infinite number of terms if you add, it is not going to impact the C1. So that is the final value. It's the final. This property is the finality property. Property of finality, whatever. It's a very nice feature in Fourier series. Otherwise, the things will be much more complicated. If the terms going to be added in future would disturb or change or tune or modulate the already previously added term, then it will be very complicated to deal with. But that luckily that doesn't happen. Okay, so you remember this thing. It is very, 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 very important property of Fourier series. Okay, so এই স্লাইডটা আমরা অলরেডি ডিসকাস করেছিলাম, অর্থোগোনালিটি সেটের কন্ডিশন, ট্রিগোনোমেট্রিক ফুরিয়ার সিরিজ আমরা ডিসকাস করেছি। আচ্ছা, এবারে দেখো এই ট্রিগোনোমেট্রিক ফুরিয়ার সিরিজের রেসপেক্টে দেখো আমরা অলরেডি আজকে আমরা একে হাউ টু ফাইন্ড আউট একেস উই হ্যাভ অলরেডি ডিসকাসড। Here also you just see how to find out an. An is the coefficient of this trigonometric Fourier series. This coefficient A0, An, Bn, etc. Just if you look into this, if you just see, if you compare this expression with this one, yes, just to see how to find out coefficient. We found out this coefficient. This is the minimization problem, and our target was to minimize the energy of the error signal. Which was the error signal? Error signal was this, and we found out the energy of the error signal and try to minimize that. We did these things in the context of correlation. Okay, so if after doing this we got this expression, which is the Cn equals to this integration from T1 to T2. That is the time interval of interest. In our case, in case of Fourier series, it would be just a time period from any value T1 up to T1 plus T0, any value, but that is the time period. That should be equals to time period. From any point you can start, but you have to stop up to going up to a time period. Or time interval or time span equals to time period. Okay, so that is why it is T1 to T1 plus T0. And look at this. This is my original signal that I'm trying to, from which I'm trying to get the coefficient xn, xt. And here also, is it also ft, and just multiplied by one of the components of that orthogonal set. Here also, look at this. Multiplied by one of the components, because n omega naught t for different values of n, different components in this orthogonal set. Look at this, in this orthogonal set, maybe cos omega 0, maybe 2 omega 0, maybe n omega 0. For different values of n, you are getting different signal from this set. And in the denominator, you were basically within that same time period, you are basically calculating the square of that component. Square of that component. Okay, which is taken from the orthogonal set. And look at here. Here also, you are doing the same thing. Square of that component, which you have taken from the set xn, which is nothing but the energy. Here also the same thing. So now the point is, so just to understand the same thing basically. So finding out the Fourier coefficient. So that is why in the previously people introduced or in the most of the literature, they introduce the concept of vectors, then they generalize for the signal, and then a specific case of that they introduce the Fourier or Fourier coefficients. But the philosophy is same. Okay, so here if we put n equals to 0, suppose for n equals to 0, so n equals to 0, when you put n equals to 0, you just see it is basically 1. Okay, so here I will get only T0. So T0 will come into the denominator. So it will be 1 by T0 for n equals to 0. It will be 1 by T0 because T0 is in the denominator. So T0, and in the numerator it will be simply xt integrated over this time period. It's simple. This is the DC term. So the DC A0 you can find out like this. For the rest of the terms, when n is not equals to 0. That's for the other values, n plus 1, plus 2, plus 3, plus 4, etc. Plus, remember one thing, this is trigonometric Fourier series. So here, n cannot be negative. Just to look at the limit, plus 1 to infinity. Because 0 is considered here, so plus 1 to infinity, it cannot be negative. Okay, just remember this thing. Look at the component in the set. All are the positive, right? This is the one-sided spectrum you are supposed to get from this. So similarly, it will be an when it will be an. So of course, it is integration from t1 to this thing, and for other values, that means when m equals to n, integration, that means in the suppose you are actually using this relation. Yes, this one. When m equals to n, which is not equals to 0, that is clearly you are getting t naught by 2. So t naught by 2. So ultimately, it is reduced to this term. So t naught by 2. So 2 goes in the numerator and t naught in the denominator. So you are getting this. And similarly for the bn. So bn means actually the term, the coefficient that is associated with the sign terms or sign components. That means here you have to multiply with the sign. Here it is sine square. But please remember one thing, sine is an odd function. So of course, in case of sine, you cannot put n equals to 0. Because if you put n equals to 0, then it will give you 0. Then it will be a problem. So the DC term cannot be found out from sine components or using sine components. Okay, from the set. To find out DC term, you have to explore cos component or use cos component. Because DC after all an even function. DC, whatever there is in the positive half is there for the negative half. Okay, so it is after all an even component, so even function. So in that sense, you can say that only the cos component has the power or the ability to define the DC term, not the sine component, because the property doesn't match. Okay, now it is another way to represent. It is sometimes it is written in the question that you have to represent in terms of compact trigonometric Fourier series. You know, it is also known to you because if an expression is written like this, a in cos n omega naught t plus b in sin n omega naught t like this, you know how to represent everything in terms of cos. In terms of cos, what you do, you basically multiply by square root of a square plus b n square and divide by this. And then the first term you defined a function, particular function, and the second term automatically comes. So it is basically the cos, a plus b kind of. So it is, and the cn, and cn is defined, as I mentioned, you have to multiply outside by square root of a square plus b n square. This is cn, and your theta will be tan inverse minus bn by a. So this is known in the HS. You have already learned this, how to do it. So here, for the consistency purpose, what they have done, they have retained the DC term, because previously we used the DC term as a naught. So to keep the similarity with the previously known things, they have used C naught to indicate the DC term. So that means here it can be represented at xt equals to C naught kept separately to indicate the DC term, in analogous to what we have already done here. Here it is like this, the DC term kept separately, and here they have clubbed these terms together and represented everything in terms of much more compact form, and that is like this: n equals to 1 to infinity cn cos n omega naught t plus theta n. But the cn can be found out from this if an and bn are given, which is the square root of a square plus bn square, and theta is basically tan inverse minus bn by n. So you know that this is nothing new, just an application in this particular context, and the mathematics is well known to you. And then with that we come to the spectra. I have already introduced the spectra, nothing new, so I'm just skipping this slide. And now look at another example. This example tells you that there is a exponential function. Actually, if you repeat this exponential within this range, suppose 0 to pi, this exponential function is not a periodic function. Please note it. It is a decaying exponential, which is not periodic. But what we are interested to make it, we are forcing it to become periodic. That means we are capturing this signal from 0 to pi and force it to repeat. Force it to repeat so that it will repeat like this. That means it's like this. Like this. So it at 0 it is 1. Okay. Then it decays like this following this relation. And at pi, whatever value of this signal will have, from that there will be sudden jump, and again it will start from 1. So like this. Now look at here. This function, if you suppose at this point, if you come from this side, this function will give you 1. If you come from this side, this function will give you this value. So there is a jump, right? There is a discontinuity. So this is a discontinuity, this age. It looks like a shortwave kind of thing. Okay, so this becomes periodic. And now I am throwing a question to you all, that suppose if I have this kind of aperiodic signal, it's just an aperiodic signal, or I am specifying a range or the interval of the signal, or I'm taking just, I'm basically extracting a particular part, a particular portion from that signal, and I'm trying to make it or bound it to become periodic, then what operation I have to do? Discrete time Fourier transform porocho, Z transform porocho, convolution porocho. Now, এবারে আমি কোশ্চেনটা তোমাদের জন্য রাখলাম। If I have any aperiodic signal and if I want to make it periodic, in general আমি এভাবে বলছি, সেটা বললে অসুবিধা কিছু, ঠিক আছে? কি অপারেশন আমি করতে হবে? মানে আমি যেটা বলতে চাইছি, এটা আরো সিম্পলিফাই করে দিই জিনিসটা। ধরো আমার কাছে একটা aperiodic signal আছে, ঠিক আছে? xt. I want to make it periodic. Dot. What mathematical operation I have to do? Okay, I'm actually just giving the question for you to think. You just think and then come up with the answer. Not now. Okay, so this is a signal. Now look at this. Within that what is the period? Period is from 0 to pi. So within this period, within this interval of this signal, so obviously if we have to find out the fundamental frequency of this signal, omega naught, we know that is 2 pi by t naught. We know that is 2 pi by t naught. And here, look at this. This is time axis. So in this time axis, this t naught is nothing but your pi. So if you put the value of pi, then it will be 2. So omega naught is basically 2 here. You have to understand. Omega naught is basically 2. Now we are going to represent that first in terms of the simple trigonometric Fourier series, where you have the a naught, n cos 2n t, because first we have found out the omega naught. So the general expression is something like this, n omega naught t. Now if we know the value of the omega naught, then we will directly put it. And we'll get the value of this n omega naught is 2nt, like b2nt, and it is for 0 to pi. True, 0 to pi, because that's the period. Now just by applying the formula a naught, that is a naught means this 1 by t naught. Again the t naught means here the period, means here for this example it is pi, and over the pi, and that is the xt. So it is xt is, what is the form of xt? E to the power minus t by 2. So this, within this range, you are integrating and you are getting this value. Similarly, you are getting the an, you are getting the bn, and all these things you are getting. So a naught, an, bn, everything you got, and you just put it here. Okay, so this is the general trigonometric Fourier series. Now you have been asked to represent it in the compact trigonometric Fourier series. Compact trigonometric Fourier series. So compact trigonometric Fourier series, we know the formula. You know the formula, how to find out Cn, how to find out theta. Just to apply that. You know, here C naught and A naught are the same. The BC term remain unchanged. And Cn square root of A square plus Bn square. We know what is An. We know what is Bn. You just do it, find out the value. And the theta and tan inverse minus Bn by N. We know what is Bn. We know what is An. Tan inverse, that do it. You can find out this tan inverse minus 4n, which is minus tan inverse 4n. and you find out all the expressions. Now you just write it in terms of the trigonometric Fourier series form, this form, C naught plus summation of this Cx cos this. So here, this is the expression. So it has been written like this, and for taking different values of n, for different values of n in following this table, n equals to 0, n 0 is a DC term, no problem, n equals to 1. So when you put n equals to 1, then you just find out, putting the value of n, you can find out it will be equals to 2t minus 75.96 degree. You can calculate all this, minus 75.96 degree. So theta n, for n equals to 2, it will be 40, and this is the angle. Again, it equals to 560. This is the angle. This is 80. So these are the different frequency for different frequency components. N equals to 1, 2, 3, 4, 5, 6. For different values, you are basically getting different frequency components, and the corresponding to that different Cn and different theta n. That means different amplitude and different phase. And now your task is to plot it. So if you plot it, you just see it is, you are plotting it with respect to the omega. You are plotting it with respect to the omega. And if you plot it with respect to the omega, then the first component, the DC component, and please remember, this will be single-sided line spectrum, because after all, it is a trigonometric series. Representation in the form of a trigonometric series. So it will be one-sided spectrum. So the DC term will give you 0.504, and straight away you can say that phase is 0. So phase is 0. And your second term, that is the omega for omega. Now look at one thing, just to see that omega, first you got omega equals to 0, then you got the next term you got for omega equals to 2, then you got for omega equals to 4, then you got for omega equals to 6, like this. And these terms are decaying so fast. This frequency component, that magnitude, look at that amplitude, they're decaying so fast, all having a positive value. Okay, fine, that is fine, but they're decaying so fast. That means, suppose this is the DC component, and it's suppose the first frequency component, the second frequency component, third frequency component, and so on and so forth. So basically, they are decaying so fast. That is, within a few components, just within a few components, you can, after adding a few components, after adding a few components, suppose this, after that you can neglect. You can simply ignore these components, because these components hardly, when they will be added, hardly going to impact the result, the overall result, hardly, because they are so small in comparison to the other values. That is the observation. As an engineer, that should be your observation. And from there, it should click in your mind that, okay, these terms are not contributing so much, not contributing significantly. There is no such major contribution. So I can neglect that, because if I neglect that, then the burden of computation will be simple, burden of storage will be simple, burden of processing will be simple, unless. So it will be very, very easy for me to handle, as well as for the system So that is why in the last class I was also telling you, as an engineer, your job is not to work with the infinite number of samples or infinite number of terms, because then rest of the life you have to spend in calculating this AKs. Okay, this is not possible. Practically, this is not possible. So whenever we do this approximation, we basically what do you say? We truncate. Somewhere we have to stop. We have to go up to certain terms. Then we have to truncate. We have to stop the operation of addition. And where we can stop, or how we can stop, these decisions can be taken based on our experience, practical experience. What is that experience? That experience is that these are the experiences we are getting. That after a certain point, after a certain number, if you keep on adding the terms, hardly it matters. That means the AKs, the amplitude of the AKs, or the values of the AKs are going to diminish. The amplitude is going to diminish or decrease such that so small, becomes so small that it actually doesn't matter whether you add or reject. Theoretically, there may be, or mathematically, there may be large number of AKs. But you just from this plot, from this value, just by noting these values or from this plot, you could observe that okay, after a certain point, suppose after this sample or this, sorry, this term, this AK, I can neglect this. From this term onwards, I can neglect because they're simply going to decrease, and they're going to decrease in a very rapid manner. So diminishes very fast. The amplitude of the AKs diminishes. So that means the higher order terms, please note, these are the higher order terms, higher frequency terms, that means the higher order terms. So the higher order terms, after a certain time, after a certain point rather, I can neglect. Because that is not going to impact your overall result as such. So this is called the truncation. That is why people deal with a finite number of components, even though theoretically there is an infinite number of components, or mathematically. But in practice, I have to deal with only the theory, finite number of components, and this is because of this reason. It is only possible because if the things could happen in other way, that is, if the number of components or higher order components, if the amplitude increases instead of decreasing, if it increases, then the things will be complicated, very complicated to deal with, because you cannot neglect the higher order terms. Then you have to consider all the higher order terms. That means how long you will consider, or up to what point you will consider. There is no limit, because up to infinity you have to consider. So then the things will become really impractical to deal with. Are you getting the point? So it is another important thing to understand. Okay. Similarly, if you plot the phase, just to look at here, initially it is 0, then you have this theta n is negative, 75.96 degree, and then like this keep on increasing. But after a certain point, you just see it almost touches the pi by 2, minus pi by 2, that's minus 90 degree. Almost touches. So that means phase is also constant. That means saturates. There is no change as such for this example. So overall, these two, as I mentioned, this amplitude as well as the phase, both together is called the phase spectrum. Both together is called the phase spectrum, and you may be asked to plot the phase spectrum. Fourier spectrum. Both together is called the Fourier spectrum. And in a question, it may be written that plot the Fourier spectrum. So that indicates that you have to plot both the magnitude as well as phase. Okay, so let me stop here for today. আচ্ছা, আমরা নেক্সট ক্লাসটা কালকে নিই, ঠিক আছে? কালকে ওই 3টে বা 3:30 থেকে।
তো কালকে প্রবাবলি আমাদের একটা ক্লাস আছে, যদি হয় তো আমি মেল করে দেব।
কটায় আছে
এক্সাক্ট জানি না স্যার, আইদার 11টা থেকে।
আচ্ছা
দাঁড়ান আমি দেখে বলছি।
আচ্ছা বলো।
দুটো টাইম আছে, একটা 11টা থেকে আর একটা 5টা থেকে।
11টা থেকে আর 5টা থেকে, মানে এটা কি 11টা থেকে হলে 5টা থেকে হবে না এরকম ব্যাপার, নাকি দুটোই হবে?
হ্যাঁ স্যার, আচ্ছা একটা যে কোনো একটা শিওর না।
আচ্ছা ঠিক আছে, 11টা থেকে হলেও তো তোমার 2 ঘন্টার বেশি তো হবে না একটা। আমি 3টা থেকে 5টা নিয়ে নেব
না স্যার,
ঠিক আছে? 11টা থেকে হলেও তোমার 2 ঘন্টা হবে, 2-2.5 ঘন্টা হবে, আর 5টা থেকে হলে অসুবিধা কিছু নেই। আমি 3টে থেকে 5টা নিয়ে নেব, ঠিক আছে? কালকে 3টে থেকে 5টা। মানে আমি আর 2-1 দিন
ক্লাসটা পরে,
আর পরে ডিলে করো না। হঠাৎ করে কোনোদিন পরীক্ষা বলে দেবে, কোনো ঠিক নেই, ঠিক আছে? আমি একটু ধীরে, ওই জন্য দেখছি আমি লাস্ট 2 দিন ধরে ধীরে পড়াচ্ছি, ঠিক আছে? আদারওয়াইজ আমি অনেকটা স্পিড আপ করে দিতাম।
পরীক্ষা পোস্টপোন হয়েছে তো?
আমি জানি পরীক্ষা পোস্টপোন হয়েছে, পরীক্ষা পোস্টপোন হয়ে গেছে, ক্যান্সেল হয়নি, ঠিক আছে? তো এবারে পোস্টপোন হয়েছে, এখন কদিনের জন্য সেগুলো কিছু নেই। হঠাৎ করে ওয়ান ফাইন মর্নিং একটা মেল করে বলে দেবে যে তোমাদের অমুক দিন থেকে পরীক্ষা। সুতরাং ওটা তো আনপ্রেডিক্টেবল একটা সিচুয়েশন, ওখানে তুমি কিভাবে কি করবে, প্রেডিক্ট করা যায় না। তো সুতরাং সেই জন্যই আমরা চাইছি যে বেশি দিন আর নেব না। আমি আর হয়তো 2টো ক্লাস 2 দিন মধ্যে বা 2.5 দিনের মধ্যে শেষ করে দেবো, ফালতু এটাকে লিঙ্গার করে লাভ নেই, ঠিক আছে? সেই জন্য আমি তাড়াতাড়ি নিয়ে নিতে চাইছি। ওই স্লো করলে আবার স্লো হয়ে যাবে।
স্যার বলছি যে এরকম একটা পসিবিলিটি হতে পারে যে আরো নতুন স্টুডেন্ট জয়েন করতে পারে।
হ্যাঁ, কি বলছো? নতুন
হ্যাঁ স্যার,
স্টুডেন্ট?
অন্য ডিপার্টমেন্ট থেকে।
হ্যাঁ স্যার, স্ট্রিম চেঞ্জ হতে
অন্য
পারে।
ডিপার্টমেন্ট
মানে
থেকে
এই
স্ট্রিম
স্টেজে?
চেঞ্জ হতে পারে। হ্যাঁ স্যার,
এই
সেই
স্টেজে?
জন্য বলছি।
হ্যাঁ স্যার।
হ্যাঁ স্যার।
এটা তো সাংঘাতিক ব্যাপার, মানে এটা তো সিচুয়েশন ডিল করা আমার পক্ষে সম্ভব না, আমার কিছু করার নেই। তোমাদের বন্ধুরা জয়েন করলে তোমাদেরই দায়িত্ব তাদেরকে ঠিক টিউন করে দেওয়া, ঠিক আছে? সেটা আমার কিছু করার নেই, এই স্টেজে আমার পক্ষে কিছু করার নেই, আই এম হেল্পলেস, ঠিক আছে? আমার কিছু করার নেই এই অবস্থায়। কি করে মানে, এ তো 2 দিন পরে পরীক্ষা, কি হবে? তোমার পরীক্ষা কয়েকটা দিন পিছিয়েছে, এই তো ব্যাপার। সেটা 1 সপ্তাহ পেছোতে পারে, খুব
এই
জোর হলে
জন্যই স্যার
স্যার এই কারণেই পিছিয়েছে, মানে যেহেতু নতুন স্টুডেন্টরা আসবে ওই জন্যই পিছিয়েছে।
ঠিক আছে বুঝলাম, কিন্তু পেছাবে কতদিন পেছাতে পারে ম্যাক্সিমাম? এটা তো তার তো টাইম লিমিট আছে। আর দ্বিতীয়ত এখন যে সিচুয়েশন, মানে তোমাদের যদি এই সেমিস্টার বেশি পিছিয়ে যায় তাহলে নেক্সট সেমিস্টার শুরু করার তো তোমার হ্যাম্পার্ড হবে, তাই না? তো ব্যাপারটা তো সেই মানে কিউমুলেটিভ এফেক্টের মতো হয়ে যায়, তাই না? একটার জন্য আরেকটা, তার জন্য আবার আরেক বাকিগুলো, তার জন্য আরো, এইভাবে করতে করতে ব্যাপারটা ট্রিগার করে যাবে সবগুলো। তো আমার মনে হয় না এতটাও হবে, জানি না, এখন বলাও মুশকিল এই সিচুয়েশনে। চারিদিকে কোভিড এই তো শেষ হয়ে গেল, আর কি বলবো। যাই হোক, ঠিক আছে, আমি তোমাদেরকে কমপ্লিট করে দিই আমার যতটা হয়, বেশি ইয়ে করে লাভ নেই। হ্যাঁ তাড়াতাড়ি, কারণ তোমরা কতদিন ধরে ইয়ে করে ফেলে রাখবো, সেই মোটামুটি অনেক দিন হয়ে গেল। আর তোমাদেরও তো একটা ইয়ে থাকে, তোমরাও তো একটু পড়বে নিজেরা, এই এত সাবজেক্ট পড়াশোনা হচ্ছে, একটু নিজেরও তো পড়াশোনা দরকার। তো আমি যদি টানা এখন 2 মাস 1 মাস ধরে নিয়েই যাই, এটা তো আর ঠিক নয় না। অনেক হয়েছে, বা লাস্টে আমাকে একটু র্যাপ আপ করে নিই তাড়াতাড়ি, আর বেশি ইয়ে করে। আর তোমাদের যে হোম টাস্ক গুলো দিচ্ছি, যেগুলো সেলফ স্টাডি দিয়েছি বা হোমওয়ার্ক দিচ্ছি, আমরা আজকেও একটা দিলাম, এরকম এগুলো একটু নিজেরা করো, দেখো, পড়াশোনা করো, এগুলো নিয়ে ভাবো, সেগুলো করতে একটু সময় লাগবে, ঠিক আছে? আর যারা বাকিরা যদি কেউ নতুন জয়েন করে, এখন তাদের কিছু করার নেই, বিকজ এটা তোমাদেরই সামলাতে হবে, তোমাদের বন্ধু, তাদের যেটুকু নলেজ আছে, বাকিটা তাদেরকে হেল্প করতে হবে। মানে আমার পক্ষে বা আমাদের পক্ষে আমি জানি না করা সম্ভব বলে মনে হয়, ঠিক আছে? যাই হোক, আমি তোমাদের নামটা প্রেজেন্ট করে নিই, অ্যাটেন্ডেন্সটা নিই।
স্যার বলছি সেকেন্ড ইন্টারনালে আমাদের মার্কস মোটামুটি কিরকম আছে?
মার্কস তো ভালো এসছে, আমি কালকে বললাম যে তোমাদের সেকেন্ড ইন্টারনালে মার্কস তোমরা অন অ্যান অ্যাভারেজ খুব ভালো মার্কস পেয়েছো, ঠিক আছে? অন অ্যান অ্যাভারেজ ভালো, বেশ ভালো মার্কস পেয়েছো, মানে আউট অফ 30 হার্ডলি, মানে একজন হয়তো কি পেয়েছো বিলো 20, আদারওয়াইজ মানে সবাই অলমোস্ট 20 অ্যাভাব পেয়েছো। 30 পেয়েছে অর্চনা, হাইস্ট পেয়েছে, একজনই পেয়েছে 30 আউট অফ 30। 29 পেয়েছো 2-3 জন, 28 পেয়েছো অনেকে 28 পেয়েছো। আই থিঙ্ক আমি যদি খুব ভুল না করি, ওয়েন্দ্রিলা আছে নাকি? ওয়েন্দ্রিলা, হ্যাঁ আছে, ওয়েন্দ্রিলা মনে হয় 28 পেয়েছে, ইফ আই এম নট রং, ঠিক আছে? সো 28 অনেকে পেয়েছো তোমরা, ঠিক আছে? 27 আছে, 25 আছে, 4 আছে, 24 অনেকে পেয়েছো। তো এরকম কিছু এরকম ক্লাস্টার মতো আছে, বাট অন অ্যান অ্যাভারেজ খুব ভালোই হয়েছে, খারাপ হয়নি, ঠিক আছে? সো ঠিকই আছে। ওই যে সাটল মিস্টেকস গুলো যেগুলো করেছো, যেগুলো আগের দিন ডিসকাস করছিলাম বা আজকেও একটা বললাম, এগুলো একটু মাথায় রাখবে আর সেইভাবে ইয়ে করবে, তাহলেই হবে। ওভারঅল ঠিক আছে, আমার এটা বলতো মানে ঠিক আছে, মোটামুটি ঠিক আছে। আচ্ছা 301, নো 301 তো নেই, সরি 303 আছো? নেই। 306
প্রেজেন্ট স্যার।
7 নেই। 8
Present, sir.
9 309, ওকে। 310
প্রেজেন্ট স্যার।
11
Present, sir.
311,
Present, sir.
okay 313 absent. 315 absent. 316
প্রেজেন্ট স্যার।
316 প্রেজেন্ট বলে, তাই তো? 316 প্রেজেন্ট, ওকে। 319 absent. 321 absent. 322 322 24 324 absent. 25
Present, sir.
401
Present, sir.
406 absent. 408
Present, sir.
411
Present, sir.
416
Present, sir.
416 হলো, তাই তো? তারপরে কত আছো? 416 এর পর 418
স্যার আমি একটু ক্লাসটা লিভ
Present,
করছি,
sir.
আমাকে একটু বেরাতে হবে স্যার, ঠিক আছে?
তোমার রোল কত বলো?
308 স্যার, বলে দিয়েছি।
ও বলে দিয়েছো, ঠিক আছে বেরি।
ঠিক আছে, থ্যাংক ইউ স্যার।
ওকে 418
আচ্ছা স্যার, প্রেজেন্ট।
আচ্ছা 419
Yes, sir.
420
Present, sir.
ওকে 425
প্রেজেন্ট স্যার।
427
Present, sir.
8
Present, sir.
9
Present, sir.
30
Present, sir.
31
Present, sir.
32
Present, sir.
433 আছে নাকি? 433 মনে নেই। 45
Present, sir.
436
Yes, sir.
7
Present, sir.
8 ওকে। কেউ কি মিস গেলে? কেউ বাদ গেছে এরকম আছো? আচ্ছা তাহলে কালকে টুমরো ফ্রম 3 PM onwards, ঠিক আছে?
Okay, sir.
ওকে।